Well, good morning, everybody. The last week, I always feel like it's cruel and unusual punishment that they make us come back after Thanksgiving. Right? Get that break, and then like we have to come back and do 2 more weeks. It's awful. What's that?
It's all exams.
Yeah, right. Yeah, it's terrible. What do the next 2 weeks look like for you guys? Like, are you having a lot of exams this week in your other classes and things? Right? Quizzes, exams, and then they're going to turn around and give you a final, right? The week after that. So you're welcome that I'm not doing that to you. I used to. Back in the beginning of my career, I did that, but I stopped seeing the benefit of it. I didn't really, other than, well, that's what I had to go through, right? That seems to be the only reason that the practice is still in place. So, and physics is comprehensive enough. Doesn't need me to go in and do it. Can you imagine if I made you do some electric field and magnetic field stuff next week? Yeah, no, not going to happen. So let's see. Thursday we take this exam. That's all, normal. And then when are we getting together during finals week? It's going to be Tuesday or Thursday. I put it on the schedule somewhere. Where did I put that? This is to be right now, right? So, okay. So we will not meet till Thursday, December 11th. Okay. So you guys who are used to getting your exams back, like, by the Monday after, you're not going to get them back till Thursday. Okay, so you're just going to have to wait. You can email me, but I'll just reply, no, I won't tell you what your score is, all that kind of stuff. But during that exam autopsy, which will be in here, okay, that's like weird, right? But we'll do the exam autopsy in here. By the time you walk out the door, you'll know what your overall grade is in the course. Those of you that have the homework done and the quiz scores in, as far as I know, your grades are as exact as they can be, right? There should be, if you have just the one exam grade left, then you can ask Canvas what you need to get in order to get whatever grade you want. So that should all be working at this point, and I think that's all I have to warn you about. What are your questions for me, either about these topics or about the homework? Yeah.
I have a question about the nuclear power.
Yeah.
Like, because I was watching that whole lecture and it was like an hour long talk about a lot of things. And I was like,
An hour long as old white guy talking for too much? It's a good question. So I don't want to give away everything. So you basically need to know how a nuclear power plant works. So it won't be any of the bomb stuff. It won't be fusion. But know what the reactor does, right? Know what its Achilles heel is. Know what the control rods do, what the moderator's for, what the fuel rods are for. It's a conceptual question, so in this sense it was, were you paying attention during that lecture, right? I could ask other types of conceptual questions about nuclear power, but I wanted to keep it relatively simple and from the information that I presented to you. So, a multiple guess question on what does the moderator do? What do the control rods do? What do the fuel rods do? What's the most important piece of equipment to keep the reactor from melting down, right? These are the questions, right? So, did that help kind of clear up some stuff there? We teachers, it's kind of weird. We have requirements for things that we're supposed to teach in a given semester, curriculum that's agreed upon at the state level, and So there's a lot more that's on that curriculum than what you get tested on, right? Ideally, we're preparing those of you that are going into medical school, we're preparing you for MCAT. We're giving you a good basis so that 2 years from now, when you go take that MCAT, you can remember a little bit of the physics portion of it. Make that portion a little bit easier. We're helping the architects with the information they need to be able to pull off their degrees. We got so many different needs in here, from computer science to whatever, that we have to cover a lot of things, but then it's like, well, but then you only asked me about 7 things on the exam. Be great if I only ask you about 7 things on the exam. So. Other questions? Yeah.
Maybe like half-life stuff.
Half-life stuff, like you want to do a problem? All right. We can make up something. I was tempted to ask ChatGPT, but let's see if we can't do a little bit better than that. ChatGPT would probably be faster at it. All right, so let's see. We can find the half-life of something, or we could use the half-life to find the age of something. Let's do the age of something, just because that's kind of a. I think I did that example in class. You did a homework problem about that one. That'll be the theme for the one on the exam, and it's a little bit more involved, so it'll at very least over prepare you. Okay, so let's see. We did carbon dating before, right? So let's do potassium dating of a rock sample. I know that, just off the top of my head, potassium 40, I don't remember what the atomic number for potassium is. Potassium 40 has a half-life, I think, of 4.7 billion years. I think that's pretty close. Let's double check. Nope, I was totally wrong. I'm thinking of something else. 1.25 billion years. I was off by 400%. Let's see. I wonder what I was thinking of. Anyway, maybe I was thinking of a different isotope of potassium. Okay, 1.25 times 10 to the 9 billion years. And now we need a rock sample. And in that rock sample, we are going to measure like a rate. Normally, we don't measure the number of atoms in a sample. Usually, we measure a rate. So now we're going to make up something, and we're going to see if this even works. Give me a number between 1 and... Nope, can't do that math in my head. Give me a number between 1 and 1,000. 42. Okay. Now give me a number that's bigger than 42. Like a lot. 84? Okay. So I like how you guys think. So we're going to do 42 becquerels per minute. So our sample, right, has that activity in it, okay? Usually what they do is they try to do something weird with the units. So let's do becquerels per minute per gram. And then, well, no, this is how they usually do it. They usually say something like, a 200 gram sample has that activity, 42 becquerels per minute. And then the sort of rate that has, the background rate for potassium. We're going to say becquerels per minute per gram. Okay? So, all right. So again, the key part here, and you're going to have to help me with the equations here. I mean, I know that the chief equation, like the equation it comes from, so I can always just rederive it, is the rate I have now was equal to the rate I started with times e to the negative lambda t, where lambda is this decay constant. It's the natural log of 2 divided by the half-life. So like those are the chief equations. But then, didn't we solve for, we solved for in class, the time portion. You take this equation here and you solve it for t. We did that in class, and it's turned out to be what? Negative natural log r over r naught divided by lambda. Did I get that right? Yeah. Woohoo! Okay, so again, this is just I just solved and rearranged the toolbox equation, the first toolbox equation there. Okay, so I got to get the decay constant, and to do that, I am going to take the natural log of 2 and divide it by the half-life, 1.25 times 10 to the 9. I still haven't gotten this thing's math mode to understand my handwriting yet. There it is. I was like, I didn't know where my natural log button was. 10 to the 9 divide. Okay, I got 5.54, 5.55. Times 10 to the negative 10 for that decay constant. And so, like the units there, right? So this is years down here, right? So technically the units come out as inverse years. I don't really need to worry about that. I just know that if I put the decay constant in years, that my answer is going to come out in years, assuming I get all the other units talking to each other. And what I mean by talking to each other, I get all the same units, right? And by same units, I mean I've got to make sure I get these rates in exactly the same units, because those will divide, right? And all those units will cancel out. The only unit I'll have left was the unit for time I had in my decay constant. And so if I have my decay constants in years, my answer will be in years. If it's in months, it'll be in months. If it's in hours, it'll be in hours, right? It just, whatever the unit is for the half-life is the unit you'll get out for the time without having to convert back and forth to standard units. All right. So let's see. Fixing the units for R. We need becquerels per minute per gram. So I'm going to take my 42 becquerels per minute. I'm going to divide by the 200 gram sample that I've got. 0.21 becquerels per minute per gram. Wow. I think we made a big mistake, but that's okay. It's just numbers. Minus, I might tell you about the mistake later. 0.21 for the rate we have in our sample now, divided by 84, the rate that we should have when it was brand new, all divided by my decay constant of 5.55 times 10 to the minus 10 inverse years, and it should all come out in the wash. 84, this is going to be bad. Yeah. Oh yeah, I got a big number too. I got to count. 3, 6, 9. Yeah, this is a problem. 10.8 times 10 to the 9 years, or about 11 billion years. Okay, so what we learned from this is Mr. Balogh's really bad at estimating rates for potassium, because this rock is twice the age of the Earth and came from the very, the universe is about 13.7 to 14 point something billion years old. So this rock supposedly formed in the first few billion years of the universe's existence, which we've never measured anything older than, I think we're down to 4-ish billion years old for rock on the surface of planet Earth, which is really hard to pull off, because one of the good features of Earth is plate tectonics, and plate tectonics recycles rock all the time. So there's portions of Australia and Africa where on the ground you can be walking around and the rocks are 3 billion years old. Just untouched by plate tectonics. It's really kind of cool. So yeah, don't take any of these numbers to heart. I obviously screwed up on the rate that it should have been. Probably much lower, like factor of 1. Let's see.
3 or 4 equations all connected.
Yeah. The process is fine. No. Yeah, 1, 2, 3, 1, 2, 3. Yeah, okay. So I should have made this rate. This should have been 1 becquerel per minute per gram. And then I would have gotten 2.7 billion years old, which is more reasonable for surface of planet Earth. You basically just saw how I make up an exam, right? Throw stuff at a page and then check the calculation to see if it's reasonable, right? Try to pick numbers that students won't get freaked out about, which is really hard to do. And then kind of work it all out. And then the next step I would do for turning this into an exam problem, I'd be like, well, what do I want to ask them about? Do I ask you to just solve for time, right? That's one way I could do it. I could say you don't know the half-life, but you do know how old the sample is, right? And so you got this equation, and so you could solve for you could find lambda. So there's lots of different questions I can ask that are using all exactly the same equations, and it's just different math that you have to do. So from this one screen, I can develop at least 3 problems that I could put on an exam, if not more, if I sat here and thought about it for a little bit. Pretty sure this one is really close to your homework problem. In your homework, they didn't use rates. I think your homework problem had number of atoms remaining or something in it, right? So it's just this is n and this is n naught, and you just use the number of atoms. You end up with the same ratios. Did that answer your question? Okay.
Wait, what was, sorry, I know.
Yeah.
What was the blue part again?
The blue part was me correcting it for being to be reasonable.
Oh.
Because with the blue up there, if I were to carry that all the way through, then this answer is 2.7 billion. So I wanted a rock that was less than the age of the Earth, so that it would be a reasonable answer. Even if you guys didn't know it, I do try to make all the numbers on an exam live within physical reality. So.
What does R and R not represent again?
The rates, those are decay rates. So there's so radioactivity is coming off the sample at a certain sort of pace, right? And that's what those are, right? There's a measurement now, and then there's a measurement of what it should be
In a certain amount.
when it started decaying.
Oh, okay.
Yeah.
So that one's the initial one?
Yeah, so R naught's the initial rate,
And then it started.
and R is the rate you have now. And T is the time that's existed between when the initial was happening and
Can it increase?
the rate. No, it always goes down.
Would you consider like R naught to be activity since it's
They're both activities.
both activities?
They can be activities, they can be number. As long as those two things have the same units, it really doesn't matter what they are.
Activities, but like necessarily has a mass component, doesn't it?
Right. So the thing is that you are always sampling a smaller portion of the bulk, right? And when it comes to, I didn't have time to talk about this in class. I'm gonna just tell you right now, 5 minutes, no longer. How do we know what the original rates are? We do. Yeah. So let's think about an animal bone, right? Animal died, let's say 8,000 years ago, right? We know we can measure in the lab very accurately the rate of carbon-14 decay in that animal's bone. Like we can nail it. But what we need is what the amount of carbon-14 was in the environment while that thing was alive. The whole thing about carbon dating, radiometric dating, is that we can measure now, and we need to know when the sample was created, or we needed to know the rate then. And what's something we know about carbon levels in our atmosphere over time? No, they change a lot. Okay? Humans are pumping carbon in the atmosphere with abandon, right? But we've actually had more carbon in our atmosphere than we do now in the past, about, was it 200 million years ago? And it fluctuates constantly, okay? Especially over long time scales, 100,000 years that carbon dating can be used for. So how do we know what the carbon content was in the atmosphere 8,000 years ago? The answer is Greenland. What's in Greenland? Ice. Where'd that ice come from? Snow. Where did snow come from? The sky, right? As the snow fell, it trapped atmospheric gas in little tiny bubbles. And as more fell on top, it compressed that snow into ice. And over, I think it's 400 to 500,000 years, the Greenland ice sheet built up to be kilometers thick, like several miles thick of ice. So what scientists have done since the 1950s and 60s is they've gone to places like Greenland and Antarctica and other places that have these ice sheets, and they've cored through into the ice, taking the cores out. They then send those cores to very cold labs, right? And they can go back and literally count year by year the layers going back 400,000 years. And in that layer around 8,000 years ago, you can pull a sample out, and trapped in that ice are little tiny bubbles of 8,000-year-old atmosphere. You sample several of those little bubbles, and you get an idea for how much carbon was in the atmosphere, and now you know what the rate of carbon-14 decay should have been when that animal died. So you have to kind of guess like how old your sample is. Typically this is done by looking at the age of the rocks around it. If there is other evidence, say the bone was found in an ancient midden, a garbage pile, right? Okay. You can look at the pottery, you can look at the textiles, you can look at the other things in that pile to get we know this is somewhere between 8,000 and 10,000 years. And then you pull samples for that. You actually don't have to pull samples anymore. You just go to, there's tables online of what the rates all were at different years. And then you run a bunch of calculations to get kind of a window, and then you see which one is most accurate when you're done. But we know to great precision what the carbon content was in the atmosphere 8,000 years ago. And so that's how we get the R naught. For potassium, it's a little bit harder, but geologists, they're always happy with error bars of like, oh yeah, this rock's 3 billion years plus or minus 250 million years, no problem. Like, do you know what happens in 250 million years? The dinosaurs come and go, right? Like it's just, that's a huge swath of time for a human being. But geologically speaking, it's only like 5-10% error bars. So astronomers are the worst when it comes to error. Like, yeah, we know where 20% of the universe's mass is. It's like, what about the other 80%? It's not that important. What? No, that's not how that works.
Okay, so R naught is fairly accurate and it's
Yep.
the closest.
Yeah, just watch out. Carbon dating can't do anything really well after 75,000 years old. So if anybody tells you they've carbon dated something and it's 600,000 years old, they don't know what they're talking about. It was probably potassium dated, but it wasn't carbon dated. The other thing is, I've seen it too often, in the age of misinformation and the post-truth world. I've seen carbon dating used as a way to say exactly when something was made. This straw blade, this coin, this piece of scripture, this whatever was made on a Tuesday, 83, and it was raining. And I was like, no, okay, wait. You can't get that precise. Like carbon dating really can't be used to date anything that's less than 1,500 years old. From 1,500 years old till now, the rate it's hard for us to measure something that's very different from what the standard rate is now. But then there's like the Dead Sea Scrolls are an amazing story. You should look that story up sometime, because the scientists, the religious scholars, and the archaeologists and the historians all came together to take the error bars on the Dead Sea Scrolls from like a decade or two, which is huge when you talk about history and politics of what was going on at the time, and they brought it down to a matter of weeks, just based on like bringing not just the carbon data, but the coins that were found with it and what they knew the cave had been used for, and like all this is really, really cool. I love it when science comes together and different disciplines that you wouldn't think would want to talk to each other can pull off something really cool. What's that? Can we do an exposure problem? Oh boy, now I'm really going to scare you because I have to make up numbers. Let's see. Give me a number. Let's do a number between 1 and 10. 10. We're just going straight for 10. Okay. Yeah, the 8s lose out. You weren't fast enough. So 10. Let's do 10 microsieverts. We'll keep it healthy. Okay. Microsieverts per hour. Okay, is what your radiation counter tells you you are being exposed to right now. Okay. How much energy would your body absorb? We'll do whole body exposure. How much energy would your body absorb in a day? How much energy would body, and we're going to go with standard human body, so we'll just say 70 kilograms, 70 to 90 kilograms for average person. It's kind of a big range. I consider myself average, even though I'm probably tiny. 70 kilograms. How much energy would the body absorb Add or ab? Doesn't matter.
That's right.
In one day. This is not an English class. I don't care. Okay. So we know it's 10 microsieverts per hour, right? And we need to know what kind of radiation is it. What kind is it? Beta. Okay, with a Q factor of 10. All right, so.
Wait, how'd you know?
What?
We're just making stuff.
We're making stuff up.
Okay.
If I don't get a specific question, I have to make stuff up. And so what you guys get to experience is stream of consciousness in Mr. Balogh's brain, right? So, yeah, I'm just making, and this probably isn't all the information I need. I'm probably going to figure out I need something else and come back and fix it and all that kind of stuff. So, all right. I did an experiment once where I had students write the exam questions. Have you ever had a class where teachers did that? No? It was a train wreck. It was an absolute train wreck. And do you know why it was a train wreck?
Because the numbers were off?
No. They made it way too hard.
Oh.
Like, I was like, holy cow, you guys want me to give you these? Let me fix that for you. Like, they were extreme. In some cases, they were either way too stupid, dumb, easy, or way too hard. There was really nothing in between. So, anyway, I gave up on that idea. What are we doing? Okay, so energy. Like, what unit involves the actual, like, energy or amount of joules? It's the gray, isn't it? Okay, so 1 gray is equal to 1 joule per kilogram. That's just sort of a definition. And then, I could have made this harder by saying how many rems. Whatever. Okay, that's just a factor of 100 off, and I can never remember which way to go. Let's see. And then a sievert, I need your help here. A sievert is a gray times the Q factor? Is that right? Okay. So if we're going to find our grays, we need our sieverts divided by the Q factor. And now we need to find out how many total sieverts we were exposed to. Because what we have is sieverts per hour, right? So how are we going to find out how much we had in a day?
24.
Okay, so we've got to do, so now, I always feel like radiation units takes us back to chapter 1, right? Like, can you convert units between things, right? So microsieverts per hour, and in 1 hour, no, in 24 hours, I can't even do chapter 1 anymore. 24 hours in 1 day, right? So this will get us the total number of sieverts in 1 day. So what is that? That's 240 microsieverts. Did I do that right? 24 times 10? Okay. In 1 day. Okay, so there's our total amount of sieverts. So to find our total amount of grays, I'm going to take my sieverts, 240 micros of them, and divide by 10, which, thank you for choosing beta. And thank me for choosing, no, Michael chose 10. You guys are great. This is awesome. 24 micro grays. Do you see how I'm just kind of carrying that micro around instead of having to write times 10 to the minus 6 all the time? Okay. So there's the number of grays. So now how do I find the total amount of energy? Convert again. I have 24 micro grays. Right? And a gray is a joule per kilogram, right? And so to get rid of the kilograms, I am going to multiply by my 70, right? Kilograms. And I'll end up with joules. Okay, so 24 times 70. 1680. Total number of joules. Again, couldn't tell you if that's a bad. I mean, 10 microsieverts per hour is definitely elevated background radiation. I wouldn't want to stay there for more than a few days, but definitely not within the range of like getting radiation sickness. That would require several months, like 100 days. Start pushing that. Microjoules. Thank you. Yeah, I failed. -1. Right there, got the unit wrong. Carried it the whole way and just didn't do it at the end. I deserve that. Deserve that -1. I can't remember who asked this question. Did I answer your question?
It's like number 5-ish. It looks like number 5 and 32.
Sure. Numbers are meaningless to me when it comes to homework assignments. Okay. Yeah, I mean, I can look it up.
Number 12 for chapter
31. Not announcements. Assignment. Where is it? Assignments. Look at all the homework you guys have done. A lot of work. Oh, please work. Please. Oh, good. Okay. What was it? 12. Cobalt, the half-life is that. Determine the activity of the radioactive material. Okay. Let's see. We've got to do this, this. Better. No, I'll just remember it's number 12. All right. All right. You know I'm old when I use the hashtag, the pound symbol, as a number symbol. No, it's a hashtag.
Oh, I said that in music and she was not happy. She's like, it was a Sharpie.
It's a Sharpie for, yeah, a long time ago. Somebody told me the other day, and I've been thinking about this, I have to agree with them. Bach was the Newton of music. It's like, if you mean by the fact that before Bach music existed, but after Bach music really existed, then yes, I'm with you. If you start saying, well, Newton was a jerk and so Bach was a jerk, I'm not with you on that one, right? So, actually don't know that much about Bach's personality, other than he was a genius at music. All right, what am I doing? Half-life, the activity of this radioactive material. So let's see. Oh boy, I might have to go look something up. Activity is a rate, and that rate is equal to the number of atoms, the number of nuclei, times the decay constant. I was going to go get my notes, and then stupid me realized I've got a solutions button right here. Okay. So they're taking, that what I needed was lambda times n. I couldn't remember if that was the correct equation. You see how teachers get to cheat? That's how we look so smart. So we can look at all the answers ahead of time. Pretend like we know what we're doing. Okay, so let's see. So I need the number of radioactive nuclei, right? And I need this decay constant. So we'll do the radioactive nuclei later because that's more chemistry. How do we get the decay constant? Yeah, the half-life, or let's see, the decay constant is equal to natural log of 2 divided by the half-life, right? They want activity in becquerels. A becquerel is a decay per second. So what does that mean about the years thing? This time I'm going to have to be careful with my units. I didn't have to be careful in the last problem because I was carrying through that micro, right? And all that kind of stuff. Nothing was really changing there. But here I do have to convert from years to seconds because they want I'm assuming they want becquerels, which is decay per second. So all of my time units have to be in seconds. So I've got to convert 5.27 years into seconds. Let's see, 1 year has 365 and a quarter days. And 1 day is 24 hours. And 1 hour has 3,600 seconds in it. That is such exciting, riveting lecture content here. I got a big number. 6 times 10 to the 3, 6, 7, 8. Okay, so.
Wait, don't we have to put how many hours in it? Oh,
We did.
never mind.
All right, so that's how many seconds that half-life is. Okay, so we got that, which means we can now find the decay constant, natural log of 2 divided by this number, 10 to the 8th. So 2 natural log. I got a decay constant of. That can't possibly be right. I made a mistake. I'm going to say it's this number. Somebody check me. 8.67 times 10 to the minus 9. Because I had a big number and a natural log of 2 is a small number and I divide by another, and it's got to be negative. Nope. I was wrong. I must have just really messed up. I got 7.99 times 10 to the minus 10. I hate numbers. Let's check it again. Natural log of 2, 1.66, e to the 8. Did you get 4.17 times 10 minus 9?
Yep.
I'm an idiot.
Wow.
4.1. I'll do 4.18 times 10 to the minus 9. All right, boy. Failure today. Let's see. That's my lambda, which I need. I need this lambda right there. Now I need to know the number. Oh my gosh, the number of nuclei in my sample. Okay. They gave me the atomic mass of cobalt-60. And so I'm going to need to use chemistry now. I need to know like molar mass, right? I need to find the number of moles I have, because molar mass Was it 6.022 times 10 to the 23 somethings? It's like the chemist's dozen, right? I need to find out how many dozen atoms I've got, how many moles of atoms I've got, right? So let's see here. How am I going to pull that off? I've got 0.29 grams. 0.29 grams. And that atomic number, right? If you take the atomic mass, in this case 59.933, got to use all the numbers, 8.9, okay, grams in 1 mole. So that U is an atomic mass unit. And the way Avogadro's number works is that you take the atomic mass unit, you call it grams. And then if you have that many grams of your stuff, you have exactly 1 mole of stuff. And, come on, thing. 1 mole is a little furry bound creature, lives in the dirt. What number did I say? 6.022 times 10 to the 23 atoms. Yeah, that's a number that's been lodged in my brain ever since chemistry happened. Okay, so now, okay, guys, do this because obviously I can't use calculator today. 0.29. I got to type in all these numbers. I got 2.9 times 10 to the 21.
Yep.
Yeah? All right, we'll go with it.
What did we just solve for?
We solved for the number of atoms. So we needed these 2 blue numbers right here. We needed this blue number and this blue number to go into those 2 spaces right there. So now I can calculate the rate. Okay? It's my number of atoms, 2.91 times 10 to the 21st. I'd have a sneaking suspicion this is all going to go wrong. Times the decay constant, 4.18 times 10 to the minus 9. Let's see, what are my units? Yeah, it's going to be decays per second, right? Or atoms per second. So, oops, I just erased what I didn't want to erase that. Oh well. 2.91. 21. 8. 9 negative. Yeah, big number. Why is my calculator not expressing in scientific notation? .2 times 10 to the 12 becquerels. And I got it, didn't I? Pretty close. 1, 2, 3. Yep, 12.1 times 10 to the 12 becquerels. And what was that? About 1 curie? What's a curie? Curie is there's 3 point what? 7 times 10 to the 10. Ooh, this is 100 curies? Oh, this is nasty. A curie is if you're holding something that's giving an activity of a curie, you're not long for this world. So, yeah, radiation therapy for cancer, I can believe it. A lot of radiation in those devices, and then they focus that radiation down to, like, some of that positron therapy stuff is pretty amazing. They can, like, focus it down to individual cancer cells. Very targeted amounts of radiation. What's that?
It's good that they'll
Yeah. Get the cancer ones, keep the other ones. The one of the misconceptions is that when somebody has cancer, they often do both chemotherapy and radiotherapy. It's just the radiotherapy typically isn't mentioned. People kind of ball the whole thing up as like chemotherapy as cancer treatments, not necessarily. What's chemotherapy? It's chemistry. It's drugs, right? It's taking medications that can go after the cancer cells. Radiation therapy is being dosed with radiation to kill the cancer cells. Sometimes you do one or the other, not both. A lot of the time you do both. Your oncologist will tell you exactly what it is you need for that particular cancer. My best friend's wife recently went through breast cancer, and she only had chemotherapy. She didn't have radiation therapy. The chemotherapy is the one that everybody associates with cancer victims and survivors. The loss of hair, the really bad like physical health during the duration of the chemotherapy. Because the chemotherapy is basically poisoning. It's really controlled poisoning of the body in the hopes. One of the things about cancer cells is that they are very metabolically active. Like they go haywire and they take up a lot of energy. And so if you can introduce chemicals, poisons, things like that to the body, the cancer cells will ingest it or metabolize that stuff much faster than your regular cells. But regular cells pay the price too, from hair follicles to organs to all kinds of stuff.
Sometimes they stop and they still get hair fall.
Yeah, and it's crazy. Dr. Karagoa, she's going through cancer treatments right now. She's one of our chemists, and lost all of her hair, all that kind of stuff. But her prognosis is good. That family, so I don't know if you guys know, we've got 2 Dr. Kawagoas in the district. Her husband teaches down in Reedley. She teaches here. They both got cancer in the same month.
Oh, wow.
She had breast cancer, he had thyroid cancer. Both of their prognoses are good. I told them, check your drinking water. I was like, something's not right there. So,
Do they have kids?
yeah, all grown. I think their youngest is still in college. Good people. Survivors too. Other questions? Yeah. You said 8? Oh, on the subject, huh? Let's see. Was it? Maybe I don't want to do it then. The answer is no, I'm not going to do it. Oh. Done. Copy. Because if you guys can't do it, then I'm not sure I can. Okay. It looks like there's a lot of numbers in here. Oh, we're back to cobalt 60 again. Yeah, cobalt 60 is pretty strong radiation. It's used not just in treatments, but also it's a source of radiation that they use to kill off microbes and spores and fungus in food products and cosmetics and things like that. So like the strawberries you buy at the store were probably radiated by a cobalt 60 source. I want to be very clear. Your strawberries are not radioactive, but on their way to the store, they passed through a radiation facility to kill off the surface bacteria and molds and fungus so that they would last longer in the supply chain. What's that?
I was going to say they always come back.
Eventually they will, but a strawberry picked from the field will go bad like before it gets to your mouth. Like practically, it's like they take it off the plant and within hours it will be moldy. There's a lot of spinach does this. There's a lot of stuff that goes through the radiation treatment. Keep us safe. Again, to be clear, your food and your mascara and everything else is not radioactive. Well, it is because it's made of dirt, but like it's not unnaturally radioactive. Shrimp? Well, the thing with seafood is that it absorbs whatever's in the water. So, were your shrimp harvested near a radioactive source of some kind? I don't know. Seafood has a way of like concentrating the contaminants, especially mussels, things like that. I know too much. Okay, a patient with a brain tumor. Multiple sources with that energy. If the activity is millicuries, what is the biologically equivalent dose delivered to the brain tumor? Oh my gosh. Biologically equivalent dose. That's a sievert, right? This is an amount, right? That's related to kind of the kind, right, of thing, but they're not. 2 gamma rays. It says gamma. Okay. So now I know the Q factor. What's the Q factor? 1. Now, they told me 2 gamma rays, but they told me the total energy in mega electron volts. Okay, so we have an activity, right, of millicuries, which is going to tell us how many, like, radioactive particles there are. And my assumption is that this 2.5 mega electron volts is the amount of energy per event. And then that's going to let me get to grays, which is then going to let me get to sieverts. Okay, so first off the bat, I got to find out, right, how much 5 millicuries is in becquerels, so that I can then determine like how many events I have happening in a certain amount of time. Okay, so now I need the conversion again between curies and what. Okay, so 5 times 10 to the minus 3 curies. Karen, did you have it 3.7? 10 to the 10, other way around. 3.7 times 10 to the 10 becquerels in 1 curie, right? Okay, so I need that number. Okay, I got 1, 2, 3, 1, 2, 3, 6, 7, 8. I got 1.85 times 10 to the 8 becquerels, right? So at 1.85 times 10 to the 8 decays per second, for every 1 decay, I'm getting 2.5 times 10 to the 6th electron volts. So electron volts is not a unit of energy that a gray cares about, right? What are the units of energy when we're calculating grays? It's joules per kilogram, isn't it? Okay. So we need to get the electron volts into joules. 1.6 times 10 to the minus, nope, other way around. In 1 electron volt, there's 1.6 times 10 to the minus 19 joules. Did I remember that conversion correctly? It's another one of those numbers that stuck in my head. Pretty sure that's it. Okay. So what is this going to leave me with? What unit do I have here? I got rid of the decays. I got rid of the electron volts. and then I have a joule per second here, right? So we'll see where that takes us. 1 point, let's see. This turns out to be 2.5, that was 10 to the 6th. Yep. And then 1.6. Multiply. I got 7.4 times 10 to the minus 5 joules every second. Okay. So that's the number of joules per second that's being delivered to this tumor. How do I find the total amount of energy? Do they give me any indication of like how long the exposure is? It says 1 hour, doesn't it? So I take my 7.4. This is like a never-ending chapter 1 problem. Times 10 minus 5 joules per second. And in 1 hour, there's 3,600 seconds. So the seconds will, and I'll have a joule per hour. And since it's just 1 hour, I know what the answer is. This is 3,600 multiply. So 0.2664 joules in 1 hour. Okay, so now I know like the total amount of energy that was delivered by this exposure. What's a gray? A gray is an energy per mass, right? So the energy, 0.2664, divided by the mass. What's the mass of this tumor? 0.15 kilograms. Gives me how many grays? 0.150. 1.776 grays. And since the Q factor is 1, this is 1.776 sieverts because it's gamma radiation, right? So the grays and the sieverts end up the same number. Please tell me that was right. What?
What?
They really want it in REM.
Oh.
To get to REM, REM's 100, so it's 176.6. Did I do that conversion right? I did that one totally in my head. I'm redeemed from my micro of earlier. Okay, so they wanted that in REM, which was supremely annoying. One sievert is equal to 100 REM, so this is equal to 177.6 REM. So what do we need to know? We needed to know a bunch of conversion factors, and we had to know that, well, yeah, a bunch of conversion factors. A becquerel was a event or a decay per second, right? And after that's really the only physics that was there. Everything else was nuclear chemistry and chapter 1 conversion problems in a long chain of conversions.
I was mad about this problem because I thought it was a half-life problem until they gave us the half-life.
Right. Yeah. You don't need the
Yeah, it was just a red herring. So.
well, they're just telling you, right, that the activity remains constant.
Yeah.
It's such a long half-life. They're only exposed for a few minutes. Yeah, it's not going to change.
Why was the first move to put it in the becquerels?
Because Curie's, right, doesn't give you the number of events per time.
What is Curie? Like what's that?
Curie is is it the American unit for activity? Yeah, a Curie by definition is that many becquerels. So it's just it's basically a scaling factor for becquerels. I had to get into becquerels because what I knew was, what they gave me was the energy per decay. And a Curie doesn't give me the number of decays, right? The becquerel does. So.
Are there specific unit conversions we should know about nuclear power?
I mean, if you want a conversion factor, I'll give it to you. Unless the question's asking you for the conversion factor, in which case I'll tell you to figure it out. But like any conversion factors, I usually put it in with the question, right? So this, I'm not about like testing you on whether or not you can memorize numbers. It's pointless. Caleb, you had a question?
Yeah, so why did you multiply the becquerels times the total energy?
Becquerels, where did I do that?
Right under where it says half-life of.
1.85 becquerels. Oh, energy per decay. Yeah, because to get to Gray's, which was going to get me to Sieverts, I needed to know the energy. Like knowing where I needed to get to was important in this problem, right? They wanted Sieverts at they wanted REMS at the end, but like they wanted this biologically equivalent or biological effective absorbed dose, right? Okay, so I knew I was ending up in Sieverts, but to get from Sieverts to anywhere, I got to go through Gray's. And a Gray is a joule per kilogram. So then I knew, okay, I have to find joules. How am I going to find joules? It's got to be coming from this mega electron volts, right, per event. It's actually 2 events, but we won't talk about that. And so, yeah, so you basically kind of like a little bit like playing a board game. You kind of have to know where you want to end up if you're going to know how to start. How many of you in here played Ticket to Ride? Yeah. Okay, really good game. It's a perfect game for illustrating, like, you kind of have to know where you want to get to before you can start building your train tracks. So. Ticket to Ride, a very excellent game. I think it's better than Settlers of Catan, but what do I know? I only have a collection of 130 board games. Yeah, build the trains across the board. You get these tickets at the beginning, these cards at the beginning that tell you like secretly where you have to build your train tracks. And so you got this idea where you kind of have to go, and you can plan on how to get there, and then it's a card game where there's some randomness to it. And then you start fighting with your other players over different train tracks. It's great. It's a good board game. It's got fighting in it. It's got crying in it. All kinds of stuff going on. Got time maybe for a quick question? Yeah,
So we only have one conceptual question.
correct.
What would be, what's
Continuing the theme.
that chapter?
I answered this question already. I'm going to tell you to go back and listen to the beginning of the lecture. Yeah, because it was asked right at the beginning.
Thank you.
You're welcome. Sorry, didn't mean to embarrass you.
Did you already talk about electron configuration?
No, I didn't. What do you want to know? What?
I mean, are we gonna need to be able to do the 1s 2t,
Possibly, yeah.
then or
You had given us a way to
Hi,
like
we
do
need
drop
to
down.
Yeah, I said electron configuration. So so give me a. We need a periodic table. Where's my 2B? Was it chapter 30 we did periodic table? Yeah, here it is. Okay, so Pick any element on the periodic table. I would not do this to you, but pick any element you want.
You don't do none of that as well.
You should do copper.
Gold.
That's a hard one.
Gold on the periodic table is O. Why the symbol? Why does it not say GL or GO or? It's the Latin, yeah, Latin for the element. So gold is atomic number 79. Okay. You want me to do out the whole thing? Because the cheat is to start at xenon, right? And not have to go through the whole rigmarole, okay, of writing down 1s2, 2s, 2p, whatever, okay? Here, I'll map it out for you. There's the 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. Why did that one go to 3 even though I'm on the 4th row? Because I got a -1 when I'm in the D block. Okay. 4p6, 5s2. How do I know it's 5? I'm on the 5th row. How do I know it's S? Because I'm right here. How do I know it's 2? Because I filled both of them. 5s2, 4d10, 5p6. I didn't write all that down because I would never make you go this high. Okay. So what I'm going to do is I'm going to write down xenon. Okay. And then I got to keep going after xenon. So after xenon, what do I got? 6s2. Okay, so I know for gold, it's xenon. No, you're right, because sometimes I mess up. So xenon means the configuration up to xenon, up to that noble gas. And then I have 6s2, which got me through there, right? Okay, now I've got to do this. This is tricky, because this square right here is actually what? This one right here, which is going to be n minus 2, so 4f14. Back to my periodic table. Where am I at now? I went through all of those. So now I'm back to here, right? And so now what am I going to get? I'm going to get 3. So I'm on the 6th row, right? So this is 5D, 1, 2, 3, 4, 5, 6, 7, 8, 9. Oops. There we go. That should be the electron configuration for gold. Now let's do one that's more along the lines of what I would give you. Okay. Yeah. So this periodic table is the one that's on your exam. This exact one, not the chemistry yellow one that every student wanders the halls of this building looking dejected as they carry it in their hand. This one. The D block starts right here. I always get screwed up by this. Is this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15? Yes. No, it's D. It's sitting right here. It's got to be 9 because this is 10. Did you look it up online? Okay. No, it's definitely 9. Because these two right here fit right there. And then you have the 14. So this is actually, these two right here, those are really tricky. Lanthanide and actinide. You know your chemistry teacher hates you if they're asking about those. They are. It depends on the periodic table. But okay, let's do one that would be more. So generally, I'll probably be asking you for an electron configuration. I generally don't really go past the top half of the periodic table. Just to keep it easier, right? So let's do antimony. Antimony, okay? Number 51 right here, right? So what would antimony be? We'll just do it on this one. that's a 5. SB. Okay. Number 51. Okay. So we'll do it from the beginning. 1s2, 2s, that's not a 2. 2s2, 2p6, 3s2. Okay, where have I gotten so far? We went, there's the 1s2. It's tricky, right? Because the helium they always put over with the noble gases. Anyway, there's 1s2, 2s2, 2p6, 3s2. What comes next? 3p6. Okay. After the 3p6 comes 4s2, and then 3d10. Okay. We got that right there. What's this one right here? That's 4p6, isn't it? So there's the 4p6s, 5s2s, 4d10s, okay, and now we got to be careful because we've gotten through all here, right? Now we get into our P block, right? So how far in the P block? 1, 2, 3. That's a P3, right? So 5P3. Full electron configuration for antimony. And then there could be variations on a theme of this. So like, what do I mean by that? I showed you one in class. Let's do sulfur. Picking all the S elements. Sulfur, number 16. Okay, so if I gave you 1s2, 2s2, 2p5, 3s2, 3, I don't remember my order anymore. I was going too fast. Comes after 3s? 3p.
Yeah.
1, 2, 3, 4. 3p5. Okay, is that a valid electron configuration for sulfur?
Wait.
Yes.
Oh,
It's not ground state,
it could be extra.
but it's valid in that we've broken none of the rules, right? A wrong one would be 1s3, 2s1, 2p5, 3s2, 3p4. That's incorrect.
This is the first one?
You can't have 3 electrons in an s orbital. So, is the number of electrons still correct for sulfur? Pretty sure. Yes. But it's still okay. The red one's okay, the green one is not.
Is another way to do this? So like I've got S2, P6, D10, F14, and so on. And then 1s, 2s, 2p, 3s.
Yeah, there's lots of different ways to do it. I like to use the periodic table just because there's always a periodic table around.
And the number of electrons is just the atomic number.
Yeah.
So you could pick.
As long as it's not ionized. I'm not going to give you any ionized stuff. All right. I'll see you on Thursday.
When does the quiz,
One last hurrah
when do the quizzes due? When do you want
by Thursday.
Thursday?
Yeah. If you have questions, come on up.